So much for having me. It's lovely to see all of you folks. So today I would like to tell you about a new version of something called symplectic annular Khovanov homology, its relationship to knot symmetry. Before I get started, let me say this is joint with Chucky Mack at Southampton and my student Shreya Magunath at Rutgers. So what's the plan? First, we want to talk about Khovanov homology and some of its friends, and then we'll get to the new invariant under consideration. Well, and I can't see you, and I definitely can't see if you're confused. So do interrupt me if you have questions. Great. So common one of our favorite invariants. So this guy is it takes a link sitting inside of S3 and assigns to it today KH of L, which will be a bigraded vector space over some field to that. And its Euler characteristic is the Jones polynomial. And what does the definition of this look like? This has a nice, extremely accessible combinatorial definition. So what is the sketch? We take some diagram for our link. Maybe we have a hop link. So we look at all of the crossings in that diagram, and we resolve them in one of two ways, labeled 0 and 1. And this gives us a set of resolutions of a link diagram into sets of circles. In this case, the resolutions look like this, related by which column they are is how many 1 resolutions we took as we move from left to right. Okay, so what's a generator of the theory? A generator of the theory is look at one of those resolutions, and to each circle you see a sign, either a plus or a minus, and that's a generator. What do the differentials look like? Differentials are maps assigned to merges and splittings of circles, and then there's some choices of signs. If we're over a field where that's relevant, there's 2 inequivalent choices. All right, so this is a very nice, accessible thing to define. You can tell a computer how to do it. You can tell your 11-year-old person how to do it. This is a theory I have tested. It went fine. But despite being combinatorial, it contains a great deal of geometric information, has proved to be a rich source of applications. So maybe the very first big one was Jake Rasmussen's reproof of the Milner conjecture using Khovanov homology. A major highlight is Lisa Piccirillo's proof that the Conway knot is not slice. Some other big things include Lenny Ng's improvement of the slice-Benedict inequality, Ian Zemke's elementary obstructions to ribbon cobordisms, and this is a sort of incomplete list of highlights. Lots of great stuff has come from this, in principle, very diagrammatic thing. It also has connections to Floer theory. At this point, this is a well understood topic, but maybe the first connection to Floer theory to be was by Ojvap and Zuboff in 2004. I showed that there's a spectral sequence from something related to the Khovanov homology of the link. We'll explain that in just a moment, to the simplest version of Heegard-Floer homology of the branch double cover of the mirror of the link. I should not use a bar. That's a bad idea. Let's use an M. Okay, so what's going on here? So first of all, I want to be careful. This is going to be over F2 for now, because I don't want to get into signs. And okay, and this tilde means that it's reduced Khovanov homology. What you need to know about that is that it has half the dimension of the original. Right, so, and what's this thing over here? This is Ojvap and Szabo's Heegard homology. This is an invariant of 3 manifolds, as you can see from the fact that we've put in something that's a 3 manifold. It comes to us from Lagrangian Floer homology. So, since we're about to ask ourselves, is there a Floer theory analog of Khovanov homology given this picture? Let's sort of review the picture, review what's going on with Lagrangian Floer homology. So there's a question coming from this. Is there a Floer theory analog? Something from Lagrangian Floer homology to Khovanov homology. Okay, so maybe let's recall the setup for Lagrangian flare homology for just a sec. This will also give me a moment to put up my hypotheses for it. Getting the sense that not teaching on Zoom has degraded my Zoom handwriting a little bit. Let me know if you can't read anything. So, all right, what's my setup? I have maybe omega, symplectic manifold. My hypotheses will be that my symplectic form is exact. So omega is d lambda for some lambda, a one form. And also there's some convexity at infinity condition that we're going to impose. So my manifold just looks like a symplectization near infinity. If you're unfamiliar with the condition, it's just going to prevent curves from bubbling off to infinity. So we have L0 and L1 are going to be two Lagrangians, so half-dimensional submanifolds on which omega restricts to 0. These guys are going to always be compact today. And I'm also going to insist that they're exact. This means that if I take that one form lambda and I restrict it to Li, then that's d of some function. And I'm going to generally want them to intersect transversely. And given all this data, what's Lagrangian flare homology? So to this triple ML0L1, one associated chain complex CFML0L1, which looks like, well, what are the generators? The generators are the intersection points of the two Lagrangians. That's finite by compactness. What does the differential count? The differential count is going to count pseudo-holomorphic strips. So maps from here I have R cross 0, 1. Into my space, such that they limit out at intersection points between the two Lagrangians, perhaps conventionally red and blue. And the limits are intersection points, and one side goes on to L0 and one side goes on to L1. And rigid strips means we're quotienting out by translation up and down, and we count the strips that satisfy some algebraic topological index condition, and that's the differential. Okay, very good. So this construction has been a source of lots of non-classical topological invariants. So we've got a bunch of invariants that fit into the picture that looks like we take some topological data, we use it to construct an auxiliary symplectic manifold, and Lagrangians, we take the Lagrangian flare homology and we show that what we get out is an invariant of the original topological data. Okay, and Hager flare homology, as mentioned a moment ago, fits into this picture. I won't tell you the full construction, but it has those steps. So with this in mind, one can ask for a construction of Khovanov homology that also fits into this picture, which is to say it's a Lagrangian flare homology or something. And in 2006, Paul and Ivan Seidel-Smith attempted to do so. They gave us something called symplectic Khovanov homology. How's this thing defined? I'm actually going to explain a reformulation of their definition that was given by Ciprian Manolescu shortly after the original definition appeared, because it happens to be amenable to writing on a blackboard and talking about without too much buildup. All right, so how are we going to construct this? We have some link we want a theory associated to it. We're going to start with a bridge diagram. So here is maybe a bridge diagram for the trefoil, a perfectly good example. So it's going to have some bridges, they're blue, and some uncrossing arcs, they're red. Maybe the one of these will be orange so that we can sort of tell them apart more easily because they're more complicated. Okay, and this lies on the complex plane. And at the endpoints of the bridges, we'll maybe name, we have K1, K2, all the way through K2n at the end. Maybe this is K2n minus polynomial that has zeros at the endpoints of the bridges. Okay, and sitting above this inside of C3, we'll look at the associated Miller fiber, which is to say we're going to look at S up here, sitting above it. That's the solutions to U squared plus V squared plus P of C is 0, sitting inside of, so we have the coordinates U, V, and Z in C3. All right, and sitting inside that, associated to each, let's start with the blue bridges. It's the same for the red undercrossing arcs. We're going to have a sphere, indeed a Lagrangian sphere with respect to the natural choice of scalar form. So sitting above maybe this blue sphere, we have this blue arc. We have a sphere defined as follows. It's a set of U, V, Z, such that Z is in, maybe I should make these, this is B1 through Bn. And our red arcs to be A1 through An. So I want my Z to be in Bi, and I want U and V to sit inside minus P of Z times R. And if you think through that, I'm restricting each U and V to be, each U and V to lie on a particular line, and then U squared plus V squared has to be a particular number, so that's a circle. So now let's look at the picture for just a sec. Just in terms of the space S, above any random point, I have a little surface. Above an endpoint, I have a singular surface. And then above this blue line right here, well, over any point in the interior of the bridge, I have a circle that's cut out by this equation. U squared plus V squared is P of Z, and they lie on this line. But over each of the endpoints, I'm just right at this 0. There's a single thing that satisfies that because P of Z is 0. So a circle over every point on the interior and a point at the ends, it forms a sphere together. All right. You say, okay, okay, you said this was going to be a Lagrangian form homology. You need to tell me a symplectic manifold and some Lagrangians that I can take the form homology of. So, and right now you have S, and you have these spheres sitting above the blue arcs, and you could similarly get spheres sitting above the red arcs. Okay, so what is our symplectic manifold going to be? Our symplectic manifold is going to be an open subset of the Hilbert scheme of endpoints on the surface S. So I will tell you which subset in just a minute. For now, it's just going to be Yn. It lives inside Hilb n of S. Okay, the Hilbert scheme's a complicated thing. No doubt it's hard to follow too much notation in a talk. It's cool that it has a map, the Hilbert-Chow morphism, to the symmetric product of n points on the surface. So that's the space consisting of n tuples of unordered points. It's singular, but that's okay. And indeed that this map is 1-to-1 away from the diagonal. The diagonal is the set of n tuples of points where you have a repeated point, which is to say that sitting inside of this, we have, just as an embedded open subset, we have sim n of S minus the diagonal. And then at the diagonal, to get from the symmetric product to the Hilbert scheme, you do some iterated blow up. You know, inside of this symmetric product minus diagonal, one would also like to notice that we have the product of all of the spheres associated to the A arcs sitting above them in S. And also inside here, we have the product of all of the spheres associated to the B arcs. Okay, so they're in the symmetric product. In theory, the points are unordered, but in fact, for each of the sets of spheres, they don't intersect pairwise, so you can order them if you like. You have the ordered product. Okay, so you've completed this junction, and you completed this juncture that I haven't told you what yn is. Now let's do that. Yn, the easiest way to tell you what it is it's the inverse under the Hilbert homomorphism of a set of points in the symmetric product that look like tuples u1, v1, z1 all the way through un, vn, zn, such that we only use any given value of z effectively once. What do I mean by that? I mean such that zi is only equal to zj if we also have ui, vi, and is uj, vj. So we're not allowed to have two different points that use the same z coordinate, that use the same z coordinate in our tuple of points. This is sometimes called the horizontal Hilbert scheme. The idea is you're supposed to think it doesn't accumulate vertically. Anytime you've got a new point, you've sort of got a different z coordinate for it. So just reminding you, z is the coordinate down here, and u and v are the coordinates up here in the sort of vertical direction. Great. So this has a natural choice of symplectic form, which agrees with the product, away from the diagonal, and with respect to which the sigma A and sigma B products of spheres are Lagrangians. And then what's symplectic Khovanov homology? Well, it's then just the Lagrangian flare homology of the correct order is sigma B, sigma A. That's just a conventional choice. All right, that's the construction. If you didn't like the construction or you're allergic to Hilbert schemes or something, that's okay. Now you just know we have some vector space that is the construction. And you should have a couple of follow-up questions. Question one should be, is it Khovanov homology? That's a great question. The answer is we don't know in general. What we do know is that over characteristic 0, it's the same. So in 2019, Mohammed Abazaid and Ivan Smith showed that over characteristic 0, these are the same. Okay, these are the same as actually slightly subtle. Khovanov homology is a bigraded theory. A priori, symplectic Khovanov homology is a singly graded theory. So you have to take some delta grading on the Khovanov homology side, difference of the gradings, and then everything matches up perfectly. All right, but there's a correct statement in there. It's unknown over finite characteristics. So for example, it's not known over F2. That's a favorite field of mine, and I like to know things over it. You say, are you sure you don't know anything more than that? Well, both theories satisfy a skein exact triangle tautologically in the combinatorial case by work of Mohammed and Ivan in the symplectic case. So I also know it for quasi-alternating rings over whatever field I like. But other than that, I don't really know very much. Okay. At this point, we come to the second question you should have, which is why would you do this? Which is to say, a combinatorial Khovanov homology, it was so simple, it was so clean, your cousin understood it. Symplectic Khovanov homology, it has this big complicated definition. You'd better expect me to have a reason that it would be worth it to you to do that. So let me give you one reason why this is nice. Okay, so one reason that this is nice is it's got a ton of geometric structure lying around. And we can try to use that geometry to understand the theory and to point our way toward what might be true on the Khovanov side, where we'd have less hints straight from geometry and using manifolds. As an example of its geometric structure, so lots of structure. So example, O2 acts on the coordinates UV used in this construction, sitting in C2. And it's easy to convince yourself that this gives you an action of O2 on the surface S. And it's still pretty easy after that to convince yourself that this gives you a symplectic action of O2 on the entire picture, which preserves the Lagrangian setwise. Okay, so that's a pretty nice set of structure. Pretty nice structure. We have a full action, and also many subsets of the action are interesting. So indeed, today we're going to be focused on Z2 actions on the theory, some of which are subsets of this O2 and some of which incorporate some additional. So before we go on and examine the ramifications of all this structure, let's have a quick digression to recall some facts from our algebraic topology class. So let's recall some stuff about Z mod 2Z actions just for a second, because that's where we're going to be focused today. So, sickle stuff. So maybe what I'm about to explain, original ideas were due to P.A. Smith. There's two Smiths in this talk, no hope for it. And we'll explain it in a way reformulated by Baruch. So maybe I have a topological space X, and I have an action tau in it. So this is just going to be a Z mod 2Z action. This is a continuous map squaring to the identity. And it comes to me and its fixed set, we'll call it X fix. So we perhaps recall that there is a spectral sequence from the cohomology of X, and I only care about F2 coefficients right now. Tensor the cohomology of RP infinity, a space otherwise known as BZ mod 2Z, so the classifying space, to the so-called equivariant cohomology with respect to the Z mod 2Z action of the space. Okay, so probably everyone is aware you can construct equivariant cohomology using the Baruch construction, but because I'm about to leave the realm of topology behind, let me tell you what that is algebraically. This is just X over F2 adjoins Z mod 2Z, treating your complex of C star of X, say the singular chain complex associated to X, which has an action of tau on it, induced by the topological action, with F2, the trivial Z mod 2Z module, so tau X by the identity on it. All right, so there's some algebraic thing that this is. And even better, if we add the hypothesis that X has the equivariant homotopy type of a finite dimensional CW complex, then we get the additional fun. So this, what is this? It's F2 adjoin theta, where theta has degree 1. So then, if we localize, which is to say if we let theta be invertible everywhere, so this becomes theta inverse, then we have an isomorphism. Oh no, I've run out of space. We'll just move this hypothesis up a tad, so I have it. This is isomorphic to the cohomology of the fixed set, again an F2. Coefficients tensored the same, what was about to become a standard 2. This implies that the total dimension of the cohomology of the whole thing in F2 coefficients is greater than or equal to the total dimension of the cohomology of the fixed set in F2 coefficients, the classical Smith inequality. Okay, great. You say that's fantastic, but bad news. We're not doing topology right now. We're doing Floer theory. Our chain complexes are coming from counting pseudo-homomorphic curves, but it turns out there's an analog of this for Lagrangian theory due to Paul and Ivan, released in 2010. So maybe I have AML 001 satisfying all of the same hypotheses as before. That hasn't changed. Additionally, having an action, order 2 action, symplectic tau star omega is omega, preserving the Lagrangians stepwise, and as I said, order 2. And if I look at the fixed sets of that under tau, so the fixed set of the manifold and the fixed set of each Lagrangian, if all of these things are connected, then it's a new symplectic manifold with new Lagrangians in it. If they're not connected, it might be several symplectic manifolds of different dimension, but today it'll always be connected. And under some hypotheses about the algebraic topology of the situation, they showed that there's a spectral sequence from the Floer cohomology in F2 coefficients, tensor the standard term, which is the localized cohomology of RP infinity, to localizing an equivariant cohomology, which they had to define for this purpose. Even just defining the equivariant Lagrangian for homology is a task. But the point is that this last page is under some hypotheses, again, the Flirt homology of the fixed set, tensored standard form, implying again a dimension inequality. Great. Maybe it's worth mentioning that the original spectral sequence is just the Lyra-Serre spectral sequence, and now we have this Flirt theoretic analog in this case. All right, so we're about to use this to analyze what happens to symplectic Khovanov homology and some variation of it under various symmetries. Now, maybe I'll take 2 seconds and persuade you that this is something we should be motivated to do. Why should we be motivated to do this? Let's suppose we don't care about symmetry at all, but we do care about questions like, are these theories the same? And we know they're the same over characteristic 0, say Q. And we don't know over F2. Equivariant cohomology over Q with respect to an order 2 action is trivial. So you'd never sort of learn anything from considering order 2 actions on over characteristic 0, and you'd never notice if your theories were different that way. But maybe if they are different over F2, despite agreeing over, say, Q, then if you dig into looking at order 2 actions on them, that's a way you might eventually be able to see that difference, because maybe they'd have different equivariant cohomology. Okay, so that's sort of motivational. Now, if we want to think about symmetries on the theory, what symmetries can I think about? Well, I can think about intrinsic symmetries, which is to say subgroups of that O2 from earlier. Here's an important one. I can think about the symmetry UVZ goes to U minus VZ. And let's think for just a sec about what I get. So maybe I'll grab my bridge diagram. So if you think for a sec about the fact that we're in the horizontal Hilbert scheme, you'll notice that the fixed set upstairs should look like it's just coming from the fixed set of the surface S itself. Now, the fixed set of S is going to be all of the points where V equals 0 upstairs, so it's U squared plus P of Z, my polynomial, equals 0. Well, the upshot of that is that the fixed set of S under this action is the branch double cover of your bridge diagram over all of the endpoints of the bridges. Okay, let's think about that for a sec. We're branching the complex plane over 4 points. If we branch the sphere over 4 points, we get a torus. And more generally, if we branch the sphere over 2 endpoints, we get a surface of genus n minus 1. So if we're branching a punctured sphere, the complex plane over 4 points, we should get a surface of genus, in this case 1, more generally n minus 1 if we have n bridges up here, but there should be 2 points missing. We'll call these Z1 and Z2. And when I take, here are my branch points, and when I then look at the pre-image of the blue arcs upstairs, now instead of a sphere, I have a circle. And similarly above the red arcs, although it's a little bit of a pain to draw those, if I start trying to draw the branch cover of this, I have a curve like this, and then I have its mirror on the blue side, and I get a red circle. Okay, so people at this point who know Hegar-Flirt homology are starting to nod along, because the thing I'm now drawing is a Hegar diagram for the branch double cover of the link, which is to say, and this observation was maybe originally made by Ciprian. So Ciprian showed that the fixed set of Yn, the symplectic manifold, the symplectic manifold for symplectic Khovanov homology under this action, it looks like the n-fold symmetric product of the surface sigma that I've drawn right here. Except that there's some divisor coming out called the anti-diagonal divisor. So it's missing some holomorphic divisor coming from the fact that we're in the horizontal Hilbert scheme, not the first thing. And it's not actually sigma, of course. It's sigma punctured by the 2 z's. So let's be a little bit more careful. So to the two Lagrangians, they look like, well, let's name these circles upstairs. Maybe this circle, these two blue circles can be beta 1 and beta 2, more generally beta 1 through beta n. And the red and orange circles can be alpha 1 and alpha 2. Maybe we'll also draw the top half of alpha 2 for the sake of seeing what's going on. Okay, and more generally alpha 1 through alpha n. And the fixed sets of the spheres under this action are the products of the alpha I and the products of the beta I. Okay, and these are very nearly the spaces for computing Haggard-Fluor homology. So Simon-Smith's localization theorem to the setting, what do you get? You get that there is a spectral sequence from the symplectic Khovanov homology of the length. Well, it should be the Fluor homology of the fixed set. Now, that's almost the Haggard-Fluor homology, except I deleted some holomorphic divisor. In this case, that induces a filtration on the chain complex by counting intersections of pseudo-holomorphic curves with the holomorphic divisor. And if I remove that divisor, that's the same thing as taking the associated graded with respect to that filtration. So this is something that we'll put a G for associated graded or something. So this is the homology of that associated graded, but it's related to the Haggard-Fluor homology of the branch double cover of, it's the mirror of the length, the way it is in the Ojot-Szabo spectral sequence. In this case, this is coming from the fact that there's a homology versus cohomology definitional flip between the two theories. Nothing exciting going on there. And then, anytime I have this is tensor F2 theta theta, it's in the usual way. Time I have the homology of the associated graded with respect to some filtration, that comes to me with an algebraic spectral sequence to the full homology of the chain complex, which in this case is the HF hat of the branch double together with, there's a two-dimensional vector space here that arises from the fact that there are two z's on that Haggard diagram. If you have more than one base point in Haggard-Fluor homology, it generates extra factors. You can think of this as there's not a reduced symplectic Khovanov homology. So the Ojot-Szabo spectral sequence goes from reduced to HF hat. Here there's no reduced, so the first page is double the size. Final page is also double the size. It's coming from this two-dimensional vector space for the extra base point. And then tensors. Okay, so this is a symplectic version of the Ojot-Szabo spectral sequence. Since the time that they did this work, there's been a sort of cottage industry of coming up with versions of the Ojot-Szabo spectral sequence and studying them, many of them possibly by people in the Zoom room. So, but this is maybe one of the first examples. Right? So maybe one other thing to mention is that this spectral sequence right here, that's not what I wanted to do. Let's get a highlighter. Well, this is fine. This spectral sequence right here, it's I think completely unknown whether it ever fails to collapse immediately, which is to say whether it's ever non-trivial. So Eamon Tweedy showed that for two-bridge links, it absolutely collapses immediately, and we sort of don't know anything about the general case. Okay. At this point, I'm going to start filling in a table. So right now our action is u v z goes to u minus v z. And we've gotten a spectral sequence that goes from KH of L to, I'll never put in the standard factor of F2 theta theta inverse in here, to something, the G is a reminder that we're the homology of an associated unit, but something related to the branch double cover, the mirror of the link. Is there an analog in regular Khovanov homology? Yes, there is. It's the Ojot-Szabo spectral sequence. Okay, moving right along. That was intrinsic symmetries. That's something you have for any link. One can also consider extrinsic symmetries. One can scroll down. All right. particular, let's start with a two-periodic link. What does that mean? It's fixed by that my link is fixed by some z mod 2z action on S3, so fixed set-wise, such that the actual fixed set of the action is an unknot disjoint from the link called the axis, usually written A. Hopefully, we've already got a perfectly good picture of a periodic link on the board. This is a picture of the trefoil as a two-periodic knot. We notice that a two-periodic knot has a diagram that I can rotate by 180 degrees and get back my original. And indeed, I can always pick an equivariant diagram like this one for a two-periodic link. Okay, very good. So in this case, let's say that for this diagram, well, I have S is the algebraic surface upstairs, Yn is the manifold in which we compute symplectic homology. Now, if I have a two-periodic link, I can consider its quotient length. That just means, well, take the quotient by the action, because the fixed set was an unknot, we're now still in S3 and we have a quotient knot. We can draw a bridge diagram for the quotient knot like this. It's just going to look like this now. Two intersections. There we go. Great. So here is L, and we'll let the quotient knot be L bar. And down here, maybe we could form the same, if we could form the same algebraic surface that we would for any bridge diagram, let's call it S bar, and form Yn bar, the horizontal Hilbert scheme of S. Now, if we have a two-periodic link, then we have some action on Yn that looks like take UVZ and send it to UV minus Z. This action is maybe called iota A in the paper that my co-authors and I wrote. All right, so this is just saying, well, you can spin the diagram by 180 degrees, send Z to minus Z, and you will have preserved S, and you will have preserved the whole picture. You can ask yourself about the fixed set of that action, and what do you get if you try to localize its equivariant coefficient. So notice for that S quotiented out by this iota A is exactly S bar. This is just the map Z goes to Z squared. And furthermore, well, let's see. If I'm looking in the n-fold Hilbert scheme of S, maybe sitting over the n-fold symmetric product of S along the Hilbert-Chen morphism, inside the n-fold symmetric product of S, I have a way of including the n/2-fold symmetric product of S bar. How do I do that? Well, anytime I have a list of points in S bar, I just take each of those points to its two lifts in S upstairs. Which is to say, I can just take a point UVZ that includes that occurs in a tuple down here. And I map it to, well, I have UV root Z and UV minus root Z. I can't tell those apart, but since it's an unordered tuple, it does not matter that I can't tell those apart. And they both occur on S upstairs. And I can do the same inclusion compatibly with this picture on the Hilbert scheme. So this is now Hilb n/2 of S. It includes into here. In both cases, I have a fixed action coming from this UVZ goes to UV C. And the fixed set is exactly the embedded copy of the manifold from downstairs. But indeed, we have the same relationship on their Lagrangians. The upshot of which is that using this, Paul and Ivan were able to show that there is a spectral sequence from the symplectic Khovanov homology of L, manifolds upstairs, the larger space, to the Floer homology of the fixed sets, which is the symplectic Khovanov homology of the quotient length, tensor F2 theta theta inverse. All right, we're going to add that one to the chart. So this action is UVZ goes to UV minus Z, and it takes us from KH simp of L to KH simp of L bar for a two-periodic link with quotient link L. And these guys are both saddles, so let's put the citation here. But you may ask, does this have a Khovanov, a combinatorial analog? Can you get the spectral sequence on the other side for ordinary Khovanov homology? The answer is no, you definitely can't. It's an observation independently of both Paul and James Cornish that the action induced by iota A on the symplectic Khovanov chain complex admits no lift to a bigraded theory, therefore no lift to combinatorial Khovanov homology. Right? So that's that. We don't know. That's kind of confusing. So a follow-up question is, what analog does exist on the ordinary Khovanov side? Analog and combinatorial KH. The answer to that is the following. In 2018, Matt Stoffrigan and Melissa John, and this was also shortly afterward recovered by Brazic, Politarchik, and Silvino, using sort of analogous methods, is that there is a spectral sequence from the Khovanov homology of the two-periodic link, tensor the standard thing that we always expect for this kind of spectral sequence, to something called the annular Khovanov homology of the quotient link. Okay, I haven't told you what that is yet. We'll get to it in just a moment. Let me tell you what their methods were. Khovanov homology has a homotopy type due to work of Lipsitz and Schicker, maybe expanded by them and Tyler Lawson, or equivalently by work of Hugh Kreis and Case. And in particular, what does it mean, a homotopy type? It means in simplified form that there's some CW complex whose ordinary cohomology is Khovanov homology. So they constructed an action on that with appropriate fixed set, and they do actual, no kidding, Smith theory to it. So the stuff that was labeled classical in the discussion earlier. So that's awesome. So you should have a couple of questions. Question one should be, what's annular Khovanov homology? Great question. So an annular link is a link together with a choice of unknotted axis somewhere in the picture. As an example, if you have a periodic link, so here's my periodic link. The fixed set of the action is an axis coming straight out of the board at you, that unknot. So for example, the most natural choice if you have a periodic link is say that the axis fixed by the action is now your annular axis, and that turns you into an annular link. But more generally, so annular link now is a link L plus an axis A, which is an unknot linked with L. We draw a picture for our annular link, a diagram, such that again the annular axis is coming straight up out of the page at you and joining up at infinity. It's represented by this little green dot right here. And what's annular Khovanov homology? I get a filtration on the Khovanov complex by drawing an arc, maybe gamma, straight out from the center point where the annular axis lies, and by computing an annular gradient by when I have some resolution of my diagram, computing an algebraic intersection number of my resolution with that purple line segment. You say, what do you mean algebraic intersection number? Didn't you destroy any notion of orientedness by resolving all your crossings? Yes, but remember that a generator is an assignment in a resolution of a plus and a minus to every circle in that resolution. That gives you a way of orienting the circles in the resolution, and that's the intersection number I mean. It's not very hard to show that this gives a filtration on Khovanov homology. If I take the associated gradient with respect to that filtration and take its homology, I get what's called the annular Khovanov. So AKH is homology of associated gradient with respect to some annular filtration. So, this was introduced by Asieta, Pertitsky, and Sikora, and then maybe reformulated in the form I'm explaining currently by Roberts. It also has some nice presentation in terms of the Hochschild homologies of braid bimodules over extended Ock algebras, some reasonably deep space due to Belyakova, Patera, and Woolley, after being conjectured by Aru, Grigsby, and Newman. So, this situation here, these two spectral sequences, I think confused quite a few people, because it seemed like the equivariant homology with respect to the action induced by a periodic knot, the equivariant cohomology maybe, was different on the symplectic side from the combinatorial side. For a while, I think it was popular to say this piece of evidence meant that maybe these two theories didn't actually agree over F2. Certainly thought that, and I think other people thought it too. Today we're going to maybe resolve that confusion. So, given this picture right here with annular Khovanov homology, it's desirable to have an annular symplectic Khovanov homology. And indeed, we have two of them at the moment. So in 2019, Chuck Mack and Ivan Smith defined some annular symplectic Khovanov homology based on the Hochschild homology interpretation of annular Khovanov homology. So it sort of works with the braid action on the cylindrical Fakaya-Seidel category. It's very beautiful technical work. Right now, currently it's defined over fields of characteristic 0. It's believed that it could be extended. But it would require some new transversality work. It's also a little bit difficult to see actions on just because of the way it's constructed. So today, we're going to construct a new theory. Second, okay, so their theory is known to be equivalent to combinatorial annular Khovanov homology over characteristic 0, following the same lines as Abizade and Smith's group. So today we're going to construct a new annular symplectic Khovanov homology, and it's going to be sort of not very technically complicated at all. It's going to be the simplest thing one could imagine that one wanted. So again, we start with the bridge diagram. And we go through our construction of S and Yn, except this time, we remove the divisor sitting over 0. We say we have an annular link. As usual, we'll have the annular axis going straight through the center, coming out of the page at you, and we're going to remove the divisor over 0. So we have maybe Hilb n of S mod, maybe the map from S to the picture is pi or something. Mod pi inverse of Sprout. Then we're just gonna continue the construction from there, and this amounts to deleting a holomorphic divisor. And counting intersections with that divisor induces a filtration on the symplectic Khovanov chain complex, and removing it is equivalent to taking the associated gradient with respect to that filtration, as usual. And the homology of that associated gradient is our invariant. So if you're sort of familiar with the theory, you should be thinking this is a really straightforward thing to do. The technical definition is not very complicated. So the first thing, of course, you need to do is check that this is a link invariant. It is. The conjecture, of course, is that it's the same thing as ordinary annular Khovanov homology. Okay, the ambitious conjecture is always, but of course the medium conjecture would be over characteristic 0. There's a causal duality reason to believe that that would be the case, but it hasn't been written up in full yet. Then you can ask, what about actions on it? Let's go back and look at some actions. One can think about intrinsic symmetries. what will happen if we think about intrinsic symmetries? Well, once again, we'll find ourselves looking at the branch double cover of our picture in the fixed set, only this time it will be missing 0. So we'll be missing an additional 2 points up here. So in particular, maybe we call these points W. Since familiar with Hegardt-Ford homology, we'll know that if you have an additional set of base points and they satisfy some basic rules of how they're arranged, you no longer have a Hegardt diagram specifying a 3-manifold. You have a Hegardt diagram specifying a 3-manifold and a knot. So in this case, the knot in question, so there's going to be a spectral sequence starting at annular symplectic Khovanov homology and ending at the knot in question is the lift of the axis upstairs. And again, we have some anti-diagonal filtration. That means that this is the homology of the associated gradient of the filtration, and then it has an additional spectral sequence to the knot flirt homology just of the lift of the axis upstairs. Okay, we're going to add that to the table. Now this is the analog of some spectral sequence on the combinatorial Khovanov side, which was proved by Lawrence Roberts. So this is us, and the analog is due to Roberts. Once again, we can also talk about extrinsic symmetries. So, and here's what happens. Now, you could be looking at the same action iota A as previously. And what will you get? You'll get sort of maybe the expected thing. You'll go from the annular symplectic Khovanov homology to the end of the whole thing to its quotient. However, there's another possible action that you could have for a periodic knot. The other action that could lift a knot, lift the action on a periodic knot. So we've had UVZ goes to UV minus Z. And the other action you could have is UVZ goes to minus U minus V minus Z. Now, if you're trying to think about this action, you'll spend a little time having a headache because what its fixed set isn't particularly obvious. But it doesn't take long to convince yourself that it has something to do with an annular theory. Why would it, even if I start at the theory for KH simp of L, and then I look at, so not starting with this dot at all, and then I try to look at what's the fixed set. Well, I can have points in the fixed set that looks like, that have 2 poles in the symmetric product that kind of look like U, V, Z, and its pair U minus V minus Z. That would be a fixed thing. That would be something that's fixed in the symmetric product, and maybe I have n over 2 pairs like it. And that's fine, and it has no problems unless Z is 0. In which case it's not fine because it's not an element of the horizontal Hilbert scheme. You can't have UV0 and minus U minus V0 as a pair of elements in a point in the fixed set. No matter if you started with the whole non-annular theory, you're going to end up not seeing anything that lies above 0 in the fixed set. So indeed, the theory of the fixed set corresponds to is annular symplectic Khovanov homology. That's a little bit more work to verify, but you've just heard the intuition. It's that you can't have anything fixed sitting above 0. And that recovers the analog of the Stoffrig and Jones spectral sequence. So let's fill in those 2 things I just mentioned here. I mentioned that if you use the same action as before, then you get maybe a thing you might have expected. You go AKH simp of L to AKH simp of L part. There is an analog of this on the combinatorial side. It's maybe due to Melissa Jump. But if you consider a different action, on the symplectic Khovanov homology, then you get the thing that corresponds to the action on combinatorial Khovanov homology. And so maybe I'll just say that I've been focusing on two periodic knots, but in fact, there's also something for strongly invertible knots. Strongly invertible knot is fixed by a Z-mod 2Z action on S3, which preserves the orientation of the manifold but reverses the orientation of the knot. So there are two fixed points. There's a somewhat complicated spectral sequence on the combinatorial Khovanov side due to Lipschitz and Sharker for strongly invertible knots, which was proved following the methods of Stoffringen and Jung. And we also recover that spectral sequence using our theory. So the thing you get is written down there. All right, and I think I'm out of things to say to you, which is good because I'm also out of time. Thank you for your attention.